So I need to open the schedule. Please give me 1 minute to go back. So if everyone is here, so we can come back to the program. So the next talk is a talk of Diego López Cámara about a short GRB breaking out of the ejected material for NS-NS merger, live and in 3D. So Diego, you can share your, oh, it's okay. So after, well, when you only 3 minutes is left, I inform you.
Okay.
Perfect, let's go.
Okay, great. So, hi everyone. I'm Diego López Cámara. And I'm going to talk about a study which I've been doing. It's mostly led by Davide Lazzati at Oregon State University. And also we've been discussing a lot with Riccardo Ciolfi at INAF in Italy, but also there's Rosalba, Perna, Brian, Bruno, and Jared. So here goes. Okay, so first of all, 1708-17 or 1708-17A, or 17th of August. So for those of you who have absolutely no clue of what this number of this date is, I tell you, you are in the wrong Zoom meeting. So move to yours. Okay, for those of us who this number does say a thing, and Roshan already showed a plot similar to the one to the left, in which there's a gravitational wave seen by LIGO Virgo, and that's this one here, and there you see the spike, and there was like 1.7 seconds later, both Fermi and Integral saw this high energy photons in hard X-rays, and so this is what we think is the neutron star merger, and here is its gravitational wave fingerprint and the first photons that come out of that signal. I'll tell you in a bit what that was. And the one to the right, this is beautiful. So this is showing both what Fermi saw, what Integral, and this green thing here is what LIGO Virgo, and their SWOPE, which is an optical, actually small scale telescope, saw the signal there. You see that little thing? It's in, I don't remember the name of the galaxy. Anyway, so when this happened, this was the celestial object that has been observed by the most amount of satellites, detectors, telescopes, you name it, in history. More than supernova 1987A, more than anything. And the really nice thing is that for the first time, this signal was seen in tons of frequencies. Of course, gravitational waves, gamma, X-ray, UV, optical, infrared, radio. And here we actually see that for this one, the signal was followed from seconds, minutes, hours, days, up to months. And now actually we've followed it up to 3 years. Okay, and think about this photons. At the beginning, we claimed directly that it was a GRB, but then looking closely to this GRB, turned out it's actually quite atypical. So first of all, it's really close. It was at around 40 megaparsecs, but as I'm showing here, both the isotropic energy, which I'm showing here, and the isotropic luminosity was really, really, really small compared to all the other either long, which is in blue, or short GRBs. So that was the first thing that struck our mind. And the second thing is, if you see, actually, I'm going to go back here, X-ray. We actually saw it. I don't know, where am I? Yeah, 9 days somewhere. So that's that's 9 days. So after 9 days, we saw X-ray, which is actually quite weird. Normally in GRBs, we see them hours or days. That was another thing which was quite atypical. And also the behavior, here I'm showing the light curve in many energy bands. And so it turns out it also was quite weird that we could see it up to 2-3 years, both in X-rays down to radio. Well, in radio we do see them, but X-rays are not, and optical are not that common. And so all this was very exciting for the theorists, and of course tons and tons and tons of models came out. And already Gerardo and Roshan mentioned like these models here. I'm not going to explain all of the models. I'm just going to say, yeah, so they called it structured jet or top hat jet, or there was also by Salafia, he claimed isotropic explosion, and then there was Murli and Nore Gottlieb choke jet, and another which was a successful. Anyway, I'm not going to get into all the details. Thing is, thanks to some a study by Murli in 2018, we actually saw, well, they actually saw, or this signal actually has superluminal motion. That it means that the Lorentz factor is of order 4. And this is like the, how do you call it? Smoking gun of a jet. So there has to be a jet. And so with that, these models were actually not consistent with Murli's observations. And so we had this signal here. And I was actually involved in one of these models. So long story short, the most plausible model involves the merger of 2 neutron stars. Here I'm showing 2 really nice simulations, and I'm gonna later show, use actually Ricardo's final snapshot for my simulations, the simulations we're doing now. And so what it is there's this neutron star merger, and then as Fabio also and Gerardo already explained, there's the evolution of this collimated relativistic jet that through internal shocks here, boom, you get gamma, and then when this shock is moving through the external medium, you get the rest of the emission, X-rays, optical, radio, whack, and so on. And thing is, so what we claimed is that it's a short GRB, but the atypical thing is that we are seeing this short GRB for the first time. We're seeing a short GRB seen off axis. The rest, we've been seeing them on axis. But this was so close that we were able to see the effects of the cocoon, like Gerardo was mentioning just a while ago. Okay, and so, also Gerardo and Fabio showed this, this result. So I'm not gonna focus too much, but I'm only saying that what we're showing here is here in the central part is the jet, the really highly energetic, relativistic, collimated jet here. And then there's this parts here of, like in the wings, that's the cocoon. And the cocoon is created simply by the fact that the jet is moving through an ambient medium, and the jet is like with plow, or these snow plows that you're moving through. I don't know if you're able to see me, but well, you're moving through the snow and you're pushing the snow to the external parts, and that's what you get this cocoon. And it turns out we are seeing this lateral snow before before it melts, and then you're able to see the snow plower. And so at the beginning, we are looking at this part, which is this C here. There's the light curve. And so we're looking at this C, boom, part here. And that's why we're getting these points here. And then we're able to see, because this is getting optically thin, then we're able to see further inside the jet. So then you get to see this B part. And so you get to see the orange part. And finally, when both the C and B are optically thin, you get to see the inner part of the jet. And though that's here A. And so we get to see that A, and that was the spike. And then the jet, because it's moving through the ambient medium, it's increasing its angle, it's diminishing its velocity, and that's why then it goes down. So what we claimed in this study is we are looking at first the cocoon, then inner of the cocoon towards the jet, and finally the jet. And that was this study. Okay, so that was really nice, 2018. And then in another study of Davide Lazzati, so it's not that simple. There's actually, and also Ariadna Murguia and Enrico Ramirez and other groups have started looking at this. Oh, God damn it, I don't have 5 minutes. And so what happens is that there's a wind that's being created in the, that's been launched in the neutron star merger. And then the jet is gonna move, but the jet is gonna interact with this wind that was moving. And then it turns out the jet, as I said, creates the cocoon. And then there's gonna be a battle between jet cocoon versus the wind that was here, that Gerardo mentioned it that's a while ago. And then once this moves up to 1,000 times bigger than this, it's optically thin, and we get to see the first emission of these photons, and that's the gamma. Okay, and of course, we're looking at this off angle. Good. So what I claim is there is no 3D study of this jet cocoon versus wind for the short GRB seen off axis, and that's where we attacked. Good. So as I said, we took this final snapshot of Ricardo that he did the neutron star merger study using general relativity and magnetic fields. And so we took this last snapshot, which I'm showing here, but this is a really small domain. So what we did is we put this small domain and we then extrapolated using this 1/r², like a wind-like ambient medium. And through there, we launch a jet. And here I'm showing it's the typical short GRB energetics. Well, with 10 to the 50 luminosity, ergs per second. Great. And so the technical boring stuff, we used Flash code, and it solves hydro with relativistic effects. It has an adaptive mesh. This really nice equation of state. And here's the domain I'm showing. I'm going to jump right into the results. And so there's the domain. And the painful part is that it's been ridiculously, it's devoured tons and tons of hours. For the numerical simulators, this is like 10 to the 7 CPU hours. That literally means we've been using 2,000 processors for like 6 months, and it is really painful. And so here's, long story short, all my, the actual movie. And so here, just for everyone, all of this is preliminary. We haven't yet done the paper, but it will come out sometime soon, hopefully. And so here what I'm showing is in green, blue, and yellow, like this part over here. That's the wind of.
Diego, you have 2 minutes.
Great. We have the wind, and here in red, that's the jet, and also the purple is like the inner part. Well, the jet also. And so we thought, let me take this thing out. We thought that the jet was gonna break out easily. And so there we're showing how the jet is moving. Yes, you see, we're twirling the jet through the image, and the jet is supposedly gonna go easily through the wind of the neutron star merger, but it turns out to not be that easy. So that's why I call it to break out or not to break out. We see that the jet actually sort of like flickers, then it goes back into activity, and actually we see that the jet, I'm gonna play it again because it's 10 to the 7 hours of CPU. So it's really, it's so painful that we have to watch it over and over again. That's all we have. And so the jet, as I'm saying, it doesn't go that easily through the wind, which is going at like 0.1 C. And hopefully, we're still running actually at this model. We only have one model. And hopefully in like this month, September, we'll be able to get the jet going finally through the wind. Okay, here there's another version. Here I'm using a slice in the central part of the jet, so I'm doing a XY cut slice. And so here you're gonna see, and actually this is gonna move, we're gonna follow the upper part of the wind, and the jet is gonna be like getting close to it. And so this is the initial condition that we took. And then through here, I don't know if you see it, we launch the jet. And so there goes the jet. And as I say, like, look, so we see the jet head, and though there's the wind, but there's tons of, I don't know if you can look at this, there's tons of shock waves in between these two. And it seems like it's gonna go through, but then it quenches, let me play it again. Like it quenches at least one time, and then also, it seems like it's gonna go through, and even like at the final part of the simulation that I'm showing, we thought it was finally gonna go out, but then also it quenches, and then it revives again. So yeah, we think, like there, in that final push, finally the jet is gonna be able to break out of this wind. And so to finish, there's gonna be much more to come. Of course, we're gonna do a lot of post-process analysis. We hope to do like, how is the energy distribution as a function of angle? And then I wouldn't say absolutely everything that we're gonna do. We're gonna do much more than just show these two beautiful simulations. And so with that, I say thank you very much. Merci, gracias, and hopefully I'll see you next year in person. Thank you.
Thank you, Diego. So there is a question of Gerardo. So Gerardo, can you ask your question?
Yes, only a technical question. In the slide 8, how many outputs you produce in these simulations? And what is the size in gigabytes?
Size of, like how much does every snapshot weigh? Or
yes.
Like half a tera.
Wow.
And we're generating plots like once every 20th of, once every 150th of a second. So we have like 600 or something like that.
Okay, so there is a question of Alejandro. Are you including magnetic fields in your simulations?
No, we're not. We're not including magnetic fields. We're not including not even rotation. We are not including GR effects. We are, there's a lot to do, but it's still like doing another simulation including magnetic fields. I don't know. I'll be able to do this 3D analysis. We are going to compare the 3D versus a 2D version, and we'll show. So that was why I was actually asking Gerardo a question that I want to respond to myself, like to see how much the difference between the 3D and the 2D are. And I sort of know what's going to be the answer, but I'll make you read the paper.
Question of Fabio, how did you get so much CPU time and where?
Yeah, in NASA's supercomputer in Pleiades. We actually asked for allocation time, and this model ate all of it, and so we had to ask yet for another allocation time. So that's why it's taking so long, because it's taking sort of a year and a half of allocation time.
Okay, so thank you very much, Diego. So I think that we will move to the next.